We've entered an era where AI coding agents write a massive chunk of the web's front end. But here's the catch. These models are optimized for one thing above all else: functional correctness. A generated page can compile, pass every unit test, and render perfectly, while still embedding terrible design choices. It might hide fees in faint microtext, use guilt-tripping language on a decline button, or make interactive elements look like plain text. And when it comes to auditing these interfaces, we're stuck in a trade-off. Human review is thorough but painfully slow and expensive. Frontier vision language models are powerful but cost-prohibitive at scale. And rule-based tools like Xcore or Lighthouse, they catch mechanical accessibility issues, but they're completely blind to dark patterns or cognitive usability violations. So how do we get scalable, design-aware auditing without breaking the bank? A new paper from UC Santa Cruz CMU tackles this head-on. They trained a lightweight 4 billion parameter vision language model to act as a dedicated UI/UX critic, using reinforcement learning to detect violations across 19 carefully defined interface principles. Let's break down how they built the dataset, why reinforcement learning was the key, and what this means for the future of AI-generated code. First, we need to understand what exactly the model is looking for. The researchers didn't just throw a bunch of rules at the model. They consolidated 19 UI principles from 3 established HCI frameworks into a single unified taxonomy. These fall into 4 families. First, accessibility, grounded in WCAG 2.2 standards, covering things like non-text contrast, semantic structure, and error identification. Second, dark patterns, like confirm shaming or hidden costs, where the interface is deliberately shaped to manipulate the user. Third, cognitive and perceptual principles, operationalizing laws like Miller's law on working memory, Hick's law on decision complexity, and Fitz's law on target size and distance. And finally, visual composition, which captures rendering-level quality like spacing consistency and content container fit. The clever part: each principle is designed to be injectable and verifiable. Some can be caught just by reading the HTML source, like missing semantic tags or wrong language attributes. But others, like visual balance or non-text contrast, only exist in the rendered screenshot. This mix is exactly why a purely text-based model fails, and why they needed a multi-modal approach. Training a reliable detector requires high-quality labels, and manually annotating principal violations across thousands of pages is prohibitively expensive and subjective. So the team took a synthetic approach. They built a controlled injection pipeline. They started with a large corpus of real web pages, classified them by domain and page type, and then regenerated them as clean, self-contained Tailwind documents. This gave them a diverse baseline with 0 pre-existing violations. Then came the core loop: inject, re-render, and verify. For each target principle, a massive 23 billion parameter teacher model would edit the HTML to introduce a specific violation. But they didn't just trust the teacher. They re-rendered the modified page, generated screenshots, and sent both the original and modified HTML and images back to the teacher. The teacher had to verify that the violation was genuinely present and perceptible at the target resolution. If it failed, they retried up to 3 times, or dropped the sample entirely. This propose and verify loop yielded a verified dataset of roughly 10,000 pages, each containing 1 to 3 confirmed violations. Because the labels are constructed by the injection itself and verified by a strong multi-modal model, the ground truth is deterministic and highly reliable. With the data ready, they moved to training. They used QN3VL4B thinking as the student model. This is a 4.6 billion parameter vision language model, split between a 4 billion parameter text transformer and a 600 million parameter vision encoder. The thinking variant is important because it produces chain-of-thought reasoning in a dedicated block before outputting structured labels. Each training sample feeds the model 2 modalities: rendered screenshots and the full HTML source code. The screenshots catch visual-only violations, while the HTML catches structural ones. For the training algorithm, they use GRPO, or Group Relative Policy Optimization, with a group size of 16 and no KL penalty. This means the model isn't penalized for straying too far from its base distribution, allowing it to adapt more aggressively to the reward signal. Instead of relying on a noisy LLM judge during training, they computed a micro F1 score directly from the model's output. This metric balances precision and recall, which is critical because the dataset is class imbalanced, with only 1 to 3 violations per page. If the model correctly identifies injected positives and clean negatives, it gets a high reward. If it hallucinates a violation or misses one, the score drops proportionally. This dense reward signal gives the policy a smooth gradient to optimize. They also trained until format compliance stabilized, which forced the model to learn concise reasoning and terminate its thinking block in time to output a parsable label set. The results speak for themselves. Before training, the zero-shot model was uneven. It caught text-heavy violations like hidden costs or trick questions, but completely failed on visual and relational principles. Non-text contrast and content container fit sat at 0%. The model was heavily biased toward reading the HTML and largely ignoring the screenshot. After continued reinforcement learning, the micro F1 score jumped from 36% to 84%. 13 out of 19 principles exceeded 80% F1. The visual-only principles saw the most dramatic gains, proving the model actually learned to leverage the rendered screenshots. Dark patterns with textual evidence, saturated near 100%. But the error analysis reveals where the frontier still lies. Three principles remain stubbornly difficult: Fitz's law, Miller's law, and misdirection. All three require a relative judgment across multiple elements. Misdirection compares the visual weight of two competing actions. Fitz's law relates a target's size and position to its context. Miller's law counts grouped items against a working memory threshold. At the 448 by 544 pixel training resolution, fine-grained spatial and counting comparisons are inherently noisy. The researchers note that higher resolution inputs or explicit region cues will likely be needed to close this gap. So why does this matter? As AI coding agents become the default for front-end development, we can't rely on unit tests alone to guarantee interface quality. This research demonstrates that a small, trainable vision language model can serve as a cheap, scalable UI/UX critic. It can run on every generated page, filter low-quality training data, or even provide a design-aware reward signal during the training of future coding agents. The team has also released their data generation recipe and injection prompts, making this fully reproducible. The path forward is clear. We need to move beyond functional correctness and bake design principles directly into the training loops of generative AI. If we can teach models to recognize not just whether code runs, but whether it respects human perception and cognitive limits, we'll finally get interfaces that are both functional and genuinely usable. Thanks for watching. If you want to dive deeper into the taxonomy, the GRPO reward setup, or the injection prompts, I'll leave links to the paper and their GitHub repo in the description. Let me know in the comments which of these 19 principles you've encountered most in AI-generated code, and I'll see you in the next one.